Good morning, everyone. Am I audible?
Yes, sir.
Yes.
Okay, thank you. Is there a question from the last lecture? Any question that you would like to ask? Okay, so let us start today's lecture. So we have to still fix the time. You can ignore it. So in the last lecture, we have looked at certain Fourier transform pairs. We have seen that the Fourier transform of delta n is 1. Okay. Fourier transform of a to the power n un is this function. Xn, if it is a rectangular function, its Fourier transform is sine by sine form. And Fourier transform of 1 is this function. You can verify that all the Fourier transforms are periodic functions, right? Because Fourier transform, a discrete time Fourier transform, is in general a periodic function. Now let us do some more Fourier transforms. Suppose xej omega is this function. Okay. What is xn for this? Xn for this function. So you remember the formula of xn? We have to divide 1 by 2 pi. Then we have to integrate in one period. We have to take xej omega in one period, multiply with e to the power j n omega, right? And integrate with respect to omega. This is how we find xn. So this 1 by 2 pi cancels with this 2 pi. And we are integrating again in the period, in this period 0 to 2 pi. Xej omega in this period is simply del omega minus omega naught, right? We can plot this function, right? So if you plot this, you will have this at omega naught, one impulse. Then the second impulse you will have at omega naught plus 2 pi. Remember, m is an integer. Then at omega naught plus 4 pi, so on and so forth. Then at omega naught minus 2 pi, right? So if I take this between one period, let's say 0 to 2 pi, somewhere here, I simply get one impulse at omega naught. I multiply by this and integrate with respect to omega. Now you know how to solve this integration, right? So we will get simply here what? E to the power j n omega naught with a minus sign. Why are we having a minus? Will we have a minus sign? Class?
No, sir.
Or not? Are you able to hear me?
Yes, sir. Yes, sir. It
Will
will
we
be a
have a
plus
minus
sign.
sign or not? How to
We
evaluate
should
this
have.
integration? We?
We should have minus sign.
Why?
But it is the formula, I guess.
Sorry?
It is the formula, right? We have a minus sign on the formula.
Oh, you are saying we have a minus here.
Yeah.
Are you sure? Do we have minus in this formula, xn?
No, sir. We have plus in the.
No, sir.
Oh, sorry.
No, sir.
We have plus, right? So remember, xn has a plus, and xej omega, which is the inner product between xn and e to the power j n omega, this will have minus. Opposite signs. So we will not have actually a minus sign, so it will be simply e to the power j omega naught n, right? Clear? Do you agree or not?
Yes, sir.
This is a typo. Yeah.
Why only the del omega minus omega naught term came? Like there would be one term only, but why only omega minus omega naught in the integral?
You can take any term.
Okay.
Let me take.
Yeah, I got it. Thank you.
Yeah, because 2 pi n, right? That is 1. It doesn't matter. So please fix this. There is e to the power plus j omega naught n, and here also. Do you understand? So if just one more second. So just remember this thing. It's an important thing. If I simply had summation delta omega minus m2 pi, what is this Fourier transform? What is this xn for this signal? What is xn? We have already done this, is 1, right? But for this signal, my xn is this. Okay, just remember this. All right. So properties of DTFT, I think you already know all these properties, so I will not derive any of them because we derived all of them in CTFT. Similar proofs, nothing different, just a recap. So linearity is satisfied. Time shift is satisfied as it is. Modulation is also satisfied as it is. We have seen all of these properties in CTFT. Conjugation is also satisfied, very similar to CTFT case. And differencing also is satisfied, right? So differencing, of course, will be different because in CTFT case, we have dxt by dt. And we have seen that this is j omega x omega. Here, we do not have this differentiation operation because the signals involved are discrete time. So rather we would take the difference rather than the differentiation of the signals. And you know that xn, if it has a Fourier transform xc j omega, this will have a Fourier transform given by the time shift e to the power minus j omega, right? Xc j omega. And so this signal, a differencing operation, will give you this DTFT. Okay, simple. Clear? Any question?
No, sir.
Yeah, is there a question? Okay, so just one caution that I will like to give you. I am presenting the caution based on differentiation, though the same thing is valid for differencing also. Because you are used to this differentiation, I present the caution with respect to differentiation. So we know that if yt is dxt by dt, listen to this very carefully. Then the Fourier transform of yt, which is y omega, we have said that this is j omega x omega, right? Now, if I use this expression, then from this expression, if I calculate x omega, then x omega will turn out as y omega by j omega. Okay, so that is one result. Now I do this thing, because if yt is dxt by dt, xt is the running integration of yt. So I also can find x omega from y omega using this relationship. So using this relationship, what I find is x omega is y omega by j omega pi y0 delta omega. Now these two answers are different, right? They are not the same. So which one is correct? Of course, this one is correct. Why this one is correct? Because in differentiation and in differencing, sometimes we kill the DC value of the signal, right? DC value of the signal is killed. And thus, you cannot go from here to here, because y of 0 in this case will be 0, right? In this case, y of 0 is 0. So if you make this as 0, then these two relationships are exactly same, right? So we cannot go from here to here. The message is we cannot go from here to here if xt has a DC value. If xt has a DC value. Right? Because if xt has a DC value, that means what?
Sir, it will get omitted when we differentiate.
Sorry?
It will get eliminated once we differentiate.
Yeah. If xt has a DC value, then on differentiation, this DC value will be killed. Right? So remember, it's important idea that however, if xt has a DC value 0, if it has a DC value 0, then of course you can go from here to here. Then there is no problem. Okay. But if xt has a DC value, certain DC value, then of course going from here to here is incorrect. Any doubt? Any doubt? Do you have? No? Fine. So let us look at one equation. Suppose I say un minus 1. This relationship we have already seen. It's an impulse function, right? You know un is like this. And 0, 1, 2, 3, 4 up to infinity. So it takes a value 1. This is un. What is un minus 1? Un minus 1 is this signal. It starts from n equals to 1. If I take the difference of un and un minus 1, of course, I will get 1 at n equals to 0, which is delta n. Okay. So I know that this expression is correct. Now let me use differencing operation. Un, let me call that it has a dtft u e j omega. Un minus 1 will have this multiplied by this. And delta n we have seen has a dtft1. Now this is correct. There is no ambiguity here. But once, now if you want to find u e j omega by dtft of delta n, and if you do something like this is going to be incorrect. Okay. Why is this incorrect? Because un has a DC value, has a mean value, right? So from this expression, you cannot go to this expression. This is incorrect. Because then we are doing a mistake similar to this thing. So we cannot find the Fourier transform of dt of un by using this thing. Okay, let us look at the same thing for CTFT also, though I haven't stressed that point at that moment, but sometimes it is confusing. So we know that delta t has a transform 1, right? Okay. Now suppose I say ut has a transform u omega, let us say dut by dt, it will has a transform j omega u omega, correct? And
Yes.
dut by dt is same as delta t. Okay, fine. Now delta t transform is 1, so 1 is same as j omega u omega. So u omega, if I simply write 1 upon j omega, then this is incorrect. Okay, because ut has a DC value, so you cannot do this. You cannot use this expression to compute u omega. Okay, so you have to be careful. So the question is, if I cannot do this, how can I find the dtft of un? That is the question. Okay, so next I have said all of this just to indicate to you that something is incorrect in using this expression. So if I cannot do this, how do I compute the Fourier transform of unit step un? That is the question. Okay, so I will highlight you the important ideas, maybe on this slide itself. Okay, suppose un, I break this down. I can always do this as even part of un and odd part of un. What is the DC value of odd part of un? It's 0, right? DC value of this signal is 0. So I can use something like this for this signal. Okay, fine. So let us see that approach. So what I will do is I will break down this un into its even part and odd part. And odd part I know has a DC value 0. So if I have to use something like this, I will do for this case. That is the idea. So let us see. What I am trying to do is to compute the Fourier transform of un. Un I have decomposed into even part and odd part. Even part of un, what is it? Even part of un. This is un plus u minus n by 2, right? Everyone knows this. What is this? Picture. Un is something like this. U minus n is something like this. Right? Amplitudes 1, amplitude 1. If I add them, the two things, I will get, what will I get? I will get 1 here and 2 here, right? If I add this, and then if I divide by 2, I will get half everywhere and 1 here, right? So I can decompose this as a constant signal half, right? And I can put one impulse of the value half at this point. Okay, so event part of un is half delta n plus half. You have to stop me if something is unclear. Any question? No. Question?
No, sir.
Okay. So all of this is fine. Now, can I find the Fourier transform of UN if this is like this? Yes, of course. What is the Fourier transform of delta n? 1. Fourier transforms are linear, right? And what is the Fourier transform of half? Half 2 pi summation delta omega minus 2 pi anything m. M is some integer. Right, so this is the Fourier transform of UEN. We have computed this. Okay. Fourier transform of UEN is this thing. So one part is done. Now for the odd part, what can we do for odd part? We know that if we take U odd n minus U odd n minus 1, what is it? What is U odd n, by the way? U odd n, this is UN minus half by 2. Let us plot this also. So this is like this, UN minus UN minus 2. So I do it slightly quickly. So you know that at n equals to 0, there will be 0, right? And then we will have this. Okay. And the amplitudes here is half. So this is U odd n. So if I subtract from that, if I subtract from this U odd n minus 1, what is this signal? So from this I subtract U odd n minus 1. So what should happen? So I will get this. So you have to remember that this is 0 and this is 1. So this is U odd n minus 1. And this is U odd n. Okay, if I subtract out these two things, then of course this part will get cancelled, right? This part also gets cancelled. So what remains is something here and something here. On subtraction, this thing gets flipped. Okay. So I will get something here and something here. Fine, with an amplitude half. So this is at 1 and this is at 0. So U odd n minus U odd n minus 1 will be this signal. Okay. Now let me say that the Fourier transform of U odd n, if I use this expression, what is it? Let me call this as this. So this will be this, right? And the Fourier transform of this quantity is half 1 plus e to the power minus j omega. Okay. So U naught e j omega is simply 1 plus e minus j omega by 2 1 minus e to the power minus j omega. This expression. So the total Fourier transform of UN is this plus this. Right, so we have to sum up these two things. Right, you can of course add. So I will not explain this. We get this as the final answer, adding these two things. Okay. Any confusion? Fine.
Yes, sir.
Okay. So we have computed Fourier transform of un. Good. Now suppose, so this is slightly advanced in the sense that we have not looked at DTFS, discrete time Fourier series, as of yet. So you have to believe me because eventually we will look at it. So suppose I have a signal like this. So if you do not know DTFS, it's also fine. Suppose I have signal like this. Okay. So we will see that this is a discrete time Fourier series, but you do not have to know this at the moment. So omega naught is some 2 pi by n, and we are summing up n minus 1 terms. So what is its Fourier transform? You know, right? We have already seen what is the Fourier transform of this signal. Fourier transform of this signal is this. Okay, we have seen this. So this thing is same as this thing, right? No problem. This 2 pi is just brought in here and everything else remains same. There's no rocket science. So just let us analyze this function and see what is happening. Okay. So I'm just analyzing this function a little bit so that you have a simpler expression. Let us look at this picture. This k omega naught, what would it do? This k omega naught will induce frequencies like 0. So there is an impulse. So it's a continuous time impulse, right? This is delta omega. It's a function of omega, which is a continuous variable. So you will have impulse at 0, omega naught, 2 omega naught, 3 omega naught because of this k. And you will have an impulse at n minus 1 omega naught also because k goes from 0 to n minus 1. Okay. Then because of this p, what will happen? There are two summations. Because of this p, what will happen? So this impulse will also be shifted to 2 pi. This impulse at omega naught will be shifted to omega naught plus 2 pi. So there will be a new impulse. And subsequently, there are many more impulses. I am just looking at two cases. So this impulse at 2 omega naught will also create an impulse at 2 omega naught plus 2 pi and 2 omega naught plus 4 pi, 6 pi, and so on and so forth. Okay. So what you will see is actually, so this is this function. I'm just plotting the impulses created by these two summations. Now let us look the simplification of this. If you have to index this impulse, do you necessarily need a p, or can this be simply indexed by k? That is what we are thinking. So this impulse at 2 pi is actually also or can be created if we choose k equals to n. Right? Because if k is n, then my omega naught is 2 pi by n. So to create an impulse at 2 pi, I could have simply also chosen k as n. So understand this again. Here I am creating all these impulses by using two variables. One is k and one is p. Okay. So now we have bunch of impulses. Now I'm saying that can we get all these impulses just by using k, and let us remove out this p because that will simplify my expression. So then I realized that this impulse could be created if I could have chosen k as n. Similarly, this impulse could have been created if I have chosen k as n plus 1, and so on and so forth. So similarly, this impulse which was created by p equals to 2 could also be created by choosing k equals to 2n. Right? So instead of this complicated expression having these two summations, what I can do is I could have simply, I have not got that expression here, but I can write it for you. I could have simple expression. So I have got rid of p, and I could create all these impulses by k going from minus infinity to plus infinity. Okay, so is this clear? So what I am doing here is I was having two summations, one for k and one for p. Now I am saying all these impulses that are created by combinations of k and p, I realized that actually they could be created simply by using k, where k goes from minus infinity to p.
How is n
Okay.
omega not equivalent to 2 pi?
Sorry?
How is n omega not equivalent to 2 pi?
Because omega naught, we have started this is 2 pi by n. Okay. So n omega naught is 2 pi.
Like, is that already known or we have inferred it?
It is already known. This is given in the question.
Okay.
And we will see that in DTFS, this is always the case. Okay. Because we haven't covered DTFS, so I'm not bringing that complexity. So I'm presenting this as it is known to us at the starting. Okay.
Yeah, okay, sir.
Any other question? So the Fourier transform of this thing is simply this thing. Just remember this. It's a simpler expression.
Sir, you have written delta minus k omega naught. Will it be something like delta omega minus k omega naught?
Oh, yeah. Sorry. Delta omega, yeah, minus k omega naught, right. Okay. Sure. And now let us look at some properties of DTFT. I will not prove these properties because we have proven these properties for CTFT. Right, the proof also remains similar. I'm just recapping some of the other properties. So multiplication, sorry, this is convolution. Okay, so convolution of two time domain signals. We know in CTFT what it was, multiplication of frequency counterparts, right? So convolution in time domain leads to multiplication in frequency domain. This is also same here, no changes. Okay, proof is similar to what we have done before. Now let us look at accumulation. So we have seen integration in CTFT. So this operation is known as accumulation in DTFT case, differencing and accumulation. What is the Fourier transform of yn? Okay, now if you have to think about this again, same as we have done in CTFT, this is actually nothing but this is the convolution of xn and un. Right, this expression is what? It is the convolution of xn and un. And so ye j omega is simply what? Xe j omega multiplied by ue j omega. And ue j omega we know is what? We have already seen is this. What is it? Yeah, hopefully it is right. Okay. So this is the Fourier transform of y omega. Simple. So we have just shown that there's nothing complicated. Okay, so you get this expression. All right. Now differentiating in frequency. If I differentiate in frequency, so this is differentiation in frequency. So nxn, n times xn, this is very useful, right? Function, at least from exam point of view, this is a useful function. So nxn will have a Fourier transform which is given by difference in frequency. Okay. Seemingly very weird questions can be created if you know this property. So the proof of this is simple. Xcj omega is given by this. So dxcj omega by d omega, simple, would have this as the transform, minus j n xn. Fine. So all this is simple. Now multiplication in time domain. Multiplication of two signals in time domain, again similar, is given by the convolution of two frequency domain signals. But now we have to have a catch, and I think this has been introduced to you in tutorials, that instead of a normal convolution, now we will have a periodic convolution. That is important because these two signals involved are periodic signals, right? Xej omega is a periodic signal, Yj omega is a periodic signal. So when we convolve to periodic signals, it is important to do periodic convolution, because aperiodic convolution will give desired results, right? So multiplication of two time domain signals, again the proof, we will not do the proof, you can do the proof yourself. Multiplication of two time domain signals is the periodic convolution of DTFT, where the period is the period of one of the signal. So for periodic signals, both these signals should have the same common period, right? Same common period. And here it is no rocket science, the period is same, 2 pi. So just take the integration over 2 pi. Okay. However, interpreting the periodic convolution is difficult. At least I cannot do this clearly in my head. I'm good at aperiodic convolution, but I'm really bad at periodic convolution, and I think you might also be bad at periodic convolution. So we have a trick to think about periodic convolution in our head. Okay. Right. So periodic convolution for me is difficult. Cannot visualize what this thing will give me. So we can play a trick in order to recast this as aperiodic convolution. I'm good at aperiodic convolution. So this is a trick that we can play if you are like me. So I can define a signal x tilde, which is same as this signal, the original signal, in a period. And this is 0 otherwise. Okay. I can take this signal x tilde, which is same as this signal in this period, and this is 0 otherwise. This is just for mathematical recasting, right? Nothing else. Now, so this expression, the original expression that we have, now this could be written like this, right? Because x tilde is 0 outside this one period. So whether you choose the limit between minus infinity to plus infinity, or 0 to 2 pi, or minus pi to pi, doesn't matter. So here we are taking the limit minus pi to pi. So instead of thinking like this, I can think it in this way. Now what is this? This is aperiodic convolution. And this is much easy to think. I will tell you with one example why it is easy to think it in this way. So let us look at this example. Suppose I have two periodic signals and I have to do periodic convolution. This is normally the sign that is used for periodic convolution. If I have to do periodic convolution, what should I do? What is the trick that I can play? So this is a periodic signal, but I remove this signal here. Okay, so I made this signal aperiodic. So that's what I am doing. So instead of doing the periodic convolution, I make one signal aperiodic by killing the signal outside a period. And then I can reduce this periodic convolution to aperiodic convolution, normal convolution. And I very easily can compute what is the convolution between this signal and this signal. I know I have to put this triangle at each position of impulse. Okay, so this is the result. So could you understand what I'm saying? So when periodic convolutions are involved, it is hard to visualize them, at least in some minds. So we can play a trick. We can reduce one periodic signal to an aperiodic signal by just having a signal in one period and killing it outside everywhere. And then I can do the aperiodic convolution of that signal with the other signal. Okay, and it is easier to understand. Okay. Understood?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. So this is what I am saying. So we can convert this. Yeah. I'm not able to hear you. I hear a feeble sound, but I'm not able to hear who is speaking in what. Okay. So the mechanics to do a periodic convolution is make one signal aperiodic and do aperiodic convolution. That's good. Parseval's theorem, again, I will not go into the derivation of this, but the results. Inner product, this is the inner product between two time domain signals. And this is the inner product between two frequency domain signals. Okay, so again, inner product is preserved. Right, preserved means what? So if you have to compute this quantity, you can compute this quantity in terms of this quantity also. Okay, right, so you can use whichever domain is more convenient to you. Just one simple question. So you know, if this quantity is 0 for some examples, you know that this quantity is also 0. Okay, that means what? If you had orthogonal signals in time domain, if time domain signals are orthogonal to each other, if inner product is 0, you know the signals are orthogonal. If time domain signals are orthogonal, it will imply that the frequency domain signals are also orthogonal. It's a very important idea. Sometimes you have complicated signals and you cannot test for their orthogonality easily. Okay, and then what trick can you play? What trick can we play is we can recast those complicated signals into other domain, time or frequency, and we can check for the orthogonality in that domain. Fine. So that is the trick that we can play. So I'm saying that suppose you have sinc functions, for example, suppose you have a complicated sinc function. You try to think about this. Suppose I have another sinc function, which is having maxima here and something like this. Suppose I ask you to find the orthogonality between these or to test whether these two signals are orthogonal. It will be very difficult exercise. Near to impossible. right? You will use a lot of maths to prove that these two signals are orthogonal. So one sinc function and another sinc function shifted. But if you can recast them in their another domain, which are rectangular functions, then you can easily prove for their orthogonality. Okay, just try to see this. Okay. Fine.
Yes.
Okay. Okay, fine. Yeah. Possibly the last slide for today's lecture. Question is, do I have to teach this DTFT? Answer is no. Because we already have talked about CTFS, continuous time Fourier series, right? If you know continuous time Fourier series, you know already everything about DTFT. Because there is duality between CTFS and DTFT. Very strong duality. So remember in CTFS, we had periodic signals, periodic continuous time. And AKs in CTFS are aperiodic, discrete. In DTFT, if you look at Xn, aperiodic and discrete, XCJ omega, periodic, continuous frequency. So you know that there is some relationship between these two things, right? And there is a very strong duality between CTFS and DTFT. So I could have finished this lecture just by saying, because we have studied CTFS, DTFT is not required. Okay, let us see what is that duality. Let us do some math. So AK in case of CTFS is this thing, right? We have already seen this expression. Now I could choose T, this capital T, as 2 pi. I could do that. Suppose the period of my signal is 2 pi. That's one specific case, right? So if the period of my signal is 2 pi, if xt has a period 2 pi, then I can simply write this as this. Okay, no problem. Now you know that I could have written this like this, because this 2 pi cancels with this 2 pi, right? Now because I know this expression and I can change this T to omega, it's just a change in variable, nothing will happen. So this becomes x omega, this becomes this, and this becomes d omega. I have not done any rocket science. What I have done is in CTFS, I have chosen xt, which has got a period 2 pi, and then by some very simple maths, I would say 11th class maths or even lower, I have got this expression of AK. Okay, now let us look at this. Xt can also be written like this in CTFS. Now when my period is 2 pi, I can write it like this, which is this expression. Again, I do the same technique. T I change to omega, I have got this expression. Now if you look at these two expressions, what do you think? What do you see? What do you see?
They're the same as DTFT.
Yes, they are same as DTFT expressions. So whatever we have studied in CTFS is valid for DTFT, and we have looked at the proofs of all these properties, right? In case of CTFS, so there's no point in repeating the proofs. Okay. And all your insights about CTFS are valid for DTFT also. We have done signals as vectors and so on and so forth. All of this is valid for DTFT. Okay, good. Today is the first lecture where I completed whatever was intended. So that's very good. Any question? We have finished with DTFT today. And tomorrow we will finish DTFS also. Because it's also it's simpler because we have seen DTFT and CTFS, so it's simpler. Okay. Any question?
So in the right hand side equation, shouldn't there be a plus instead of minus?
Yeah, you are right. Yes, you are right. Perfectly right. So this has to be plus, 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 plus. Yeah, you are perfectly right. So we get these two expressions, but again, they are similar to DTFT. So if this is plus, this has to be minus, right? So we have seen this. So this is a typo, nothing else. Something happens when I make these slides. Yeah. Thanks. Any other doubt? It's good. You are correcting my slide. So next time, probably I will not have these mistakes. That's why it's very important to participate in online learning, because then I also get some feedback and my teaching improves over the years. Imagine a situation if I was just teaching like this without any participation of students, what would happen to me? There is no fun in teaching, right? So it has to reciprocate from both sides. Participation helps, it motivates teachers, get him corrected at several places, helps him to learn. Okay, so that's why I thank you all, because you are coming and doing these online classes. It's really helpful to me as well. So thanks for that. Anyways, any other question? Okay, thank you so much. See you tomorrow.
Thank you, sir. Thank you, sir.